Hi, Science 10. So what I want to do right now is go over the last section of that little mini unit we did on radiation. And then what I'll do afterwards is I'll give you the take-home quiz that you can complete and hand in for Monday. So it's a small take-home quiz. It shouldn't be, it's not going to be as long as the chemistry take-home test. So let's go through the answers here. Okay, so fission is defined as splitting of a heavy nucleus into lighter nuclei, and that can be done deliberately or it can happen on its own. So again, when we say something is radioactive, what we're saying is it's unstable, and basically what that means is the nucleus in itself can't hold itself together. Remember, in the nucleus, what you have are protons and neutrons. The protons are fixed, so every element has a specific number of protons regardless of what isotope it is, what mass number it is. So the only thing that fluctuates is the number of neutrons. And so sometimes what happens is when you have too many neutrons in there, you sort of have a bulging effect, and they want to be able to break out. And that splitting or fragmenting is what we mean by fission, right? It's just starting to break apart. Fusion is the opposite process, which we'll get to in just a moment here. And the fission process typically is accompanied by a large amount of energy, and that's what you would do in a nuclear reactor. You would basically have a chain reaction, a controlled chain reaction of fission reactions, and as that is occurring, it's going to generate a lot of energy, a lot of heat, which then can be converted to electricity. And this is a very powerful method of energy formation. Like if you, when you were looking online, you probably came across some type of relative equality between amount of, say, burning coal and amount of fissionable material. And basically the equivalence between the two is like dump trucks full of coal are equivalent to like teaspoons of fissionable material. That just gives you an idea how much energy is contained in the nuclear material. Subatomic particles are also emitted from the nucleus. So we talked about alpha, beta, gamma. Beta is an example of an electron, but protons and neutrons can also be emitted. Like I said, we can deliberately start a fission process, and that is called inducing the nucleus. So basically, it's hitting the nucleus with some small particle that essentially breaks the big nuclei. And so these are the symbols: proton 1 1, so mass number 1, atomic number 1. Neutron 1 0. Again, a chain reaction is, and I'll show you with an illustration, is basically when you have the fissionable products producing more neutrons that then go after other large nuclei and break them apart. And so we have a reactor in Canada that's called the CANDU reactor, which is, again, converting fission reactions to electricity. Fusion is sort of the opposite of fission. It's when you have light nuclei that come together, and that process produces a lot of energy. And so where this occurs would be in stars. So the sun would be an example of where this would occur. So a comparison between the two, fission and fusion. So again, fission, the description is a large nuclei splitting into smaller nuclei. Fusion is a light nuclei joining together, produced as a result of this nuclear process. So both of these produce a lot of energy. The products, radioactive. So some of the fission products could be radioactive. The fusion ones are not. Needed for the nuclear reaction to occur. So for the fission, you need to bombard the large nuclei. for the fusion process, you need a lot of heat to get the reaction initiated. Fission reactions occur in reactors and atomic weapons, and the fusion process occurs in stars. And then we'll get to the examples on the last page. Okay. So here's an illustration of fusion. You've got light nuclei here joining up, producing the daughter isotope, and then an additional neutron. Okay, and so here this would be your energy. And then for the fission, so you have a neutron or any other small particle that's basically going to hit. This is your large nuclei, heavy nuclei, so something like uranium-235, and then this is going to split, and so these are your daughter isotopes, so they can be a variety of different things. Again, you've got a lot of energy that's produced, and so here you see what's happening is you get these 3 additional neutrons that are produced, and so now what these are going to do is they're each going to attack any available large nuclei, and then and this is just going to continue to fan out, and so again that's what we call a chain reaction. Okay, and so here's the equations. So again, this would be an example of a fission reaction. There's your U-235. Your neutron hits the U-235. It breaks off into these 2 isotopes, and then here's 3 neutrons that are produced plus energy, right? And so that's your fission, and then here's an example of the fusion. 2 light nuclei like this. You can see the mass numbers here are really small in comparison to something like U-235. They join up, and then again you get a lot of energy being produced. Okay, so fuse means to come together. Fission means to break apart. And again, when I'm saying things like uranium-235 or hydrogen-2, that refers to the mass number. Okay, so the mass number is variable, right, for different isotopes, but the atomic number is fixed. So it doesn't matter if I'm talking about uranium-235 or uranium-238, they're all going to have 92 protons. Okay, so the mass number can change, but the protons cannot. Remember, mass number is equal to your number of protons plus your number of neutrons, and this is the atomic number, which is the same as the number of protons. And so for some of these ones here, like finding out what the element is, for these ones as well, you have to look at the number at the bottom, which is the atomic number, and then go on your periodic table and find out like what is number 46. That's going to be PD, right? So that's how we've determined what the element is that goes with it. Okay, so let me know if there's any of these you need further elaboration on. The attachment will be the take-home quiz, which will be on this unit, and then let's make that due for Monday, and then we'll start the next topic, which will be beginning the physics unit on motion, velocity, acceleration. Okay, so that's sort of the final. I think that's the final unit we need to be going through. So we will be able to get through the entire course before the end of the semester. Okay, so whatever that's going to look like. Okay, so again, stay safe and let me know if you have any questions. Okay, I'll talk to you again on Monday. Okay, bye now.